The antibiotics are naturally occurring compounds that are effective against bacteria. Antibiotics are produced by a variety of microbial cells. They're produced by fungal species and also by certain bacterial species. Remember, the microbe produces antibiotic in order to protect itself against other microbes. We've done a lot of research looking for antibiotic compounds that we can use in clinical medicine. Unfortunately, less than 1% of all of the antibiotics that have been discovered have proven to be useful to us. And there's a couple of reasons for this. One of the biggest is that the antibiotic has to be able to get into the cells. So if human cells won't take it up, it's not going to be effective. The other really important issue is toxicity. As we've discussed, an effective antimicrobial compound has to be selectively toxic. And unfortunately, a lot of natural antibiotic compounds are actually toxic to human cells. One of the more modern advancements, though, in antimicrobial development is the creation of what are called semi-synthetic antimicrobials. So if you recall, this is the third grouping of these antimicrobial drugs. There are purely synthetic antimicrobial drugs. There are antibiotics, the ones that are made out in nature. And then there are semi-synthetic drugs. And a semi-synthetic is just an antibiotic that has been taken into the laboratory and modified. It's had chemical groups attached to it, or it's had its chemical structure changed just enough to make it a more effective drug. Now, when we talk about the antibiotics and really the antimicrobials as a group, one of the ways that we can break them up is to talk about their spectrum of activity. And all that refers to is their effectiveness against gram-positive versus gram-negative organisms. So, broad-spectrum antibiotics, in fact, broad-spectrum antimicrobials, are effective against both types of bacteria, both gram-positive bacteria and gram-negative bacteria. They have a broad spectrum of activity. In comparison, narrow spectrum drugs are effective against one or the other. There are some narrow spectrum antimicrobials that are effective against gram-negatives, and there are others that are effective against gram-positives. So I'd like to switch gears here and talk a little bit about the mechanism of action of some of the more common antibiotics and antimicrobials. I have a list here of the ways that these drugs function inside microbial cells, bacterial cells in particular. There are 5 listed here. We're going to focus on the ones that are in red. So some of these drugs interfere with cell wall synthesis. We've already talked a little bit about this in previous lectures. There are drugs that can interfere with membrane synthesis, some that interfere more broadly with lipid synthesis. There are those that can interfere with transcription, those that can interfere with translation, and they can interfere at different points in translation, with the large ribosome subunit, or with the small ribosome subunit, or with the tRNA molecules involved in translation. So there are lots of different targets of antimicrobial drugs. And again, we'll talk about the 3 that are listed in red here. Let's begin with cell wall inhibitors. The naturally occurring cell wall inhibitors come from fungal cells. Now, you may have heard of drugs like penicillin, described as beta-lactam antibiotics. This terminology refers to a portion of the structure of the penicillin molecule. If you look at the drawing over here on the right, what's highlighted in red here is called a beta-lactam ring. And this is actually the part of the molecule of penicillin that gives it its name as a beta-lactam antibiotic. There are other antibiotics that are also beta-lactam type. The cephalosporins, for example, have this beta-lactam type of ring, and other penicillin type drugs also fall into this group. So amoxicillin and ampicillin and so on. We've talked about cell wall inhibition earlier in the course, but if you recall, the way these drugs work is by binding to one of the enzymes that's involved in the synthesis of peptidoglycan. And it's right at the end of the process. These drugs bind to the enzyme called transpeptidase. Remember that transpeptidase is the enzyme that cross-links peptidoglycan. After the strands of NAG and NAM are made, recall that there are short chains of amino acids jutting off of those chains. And transpeptidase is going to join the amino acid chains together, creating these cross bridges that give peptidoglycan its great strength. So the beta-lactam antibiotics are actually interfering with that process by binding to that enzyme. The original beta-lactam was penicillin, and it actually is still used today. It's quite an effective antibiotic in certain clinical situations. The original molecule goes by the name penicillin G. Penicillin is actually a narrow spectrum antibiotic. It's effective against gram-positive bacteria. Unfortunately, there's been a fair amount of resistance that has developed over the years to penicillin G. These bacteria, the bacteria that have become resistant to penicillin, have mutated and now produce a protein, a resistance protein called beta-lactamase. So bacteria that are resistant to penicillin can make an enzyme, beta-lactamase, that cuts the beta-lactam ring in the penicillin. And when that ring is cut, when it's destroyed, the penicillin can't do its job. It can't stick to the transpeptidase enzyme and inhibit it. Now, the other penicillins, including drugs like amoxicillin and ampicillin, are semi-synthetic. So penicillin G was taken into the laboratory and it was chemically modified to create drugs like ampicillin and amoxicillin. What makes ampicillin and amoxicillin different is that they can be transported across that outer gram-negative membrane, while the original penicillin can't. So they are now effective against gram-negatives and gram-positives. In other words, ampicillin and amoxicillin have a broad spectrum of activity. There are several other penicillin type antimicrobials, and they are used in different clinical applications. For example, there's a penicillin type drug called methicillin, and methicillin is sort of famous for its association with MRSA. Methicillin is also semi-synthetic. It was a penicillin G molecule that was taken into the laboratory and modified to create methicillin. And methicillin was never applied very widely in medicine. It was reserved to be used for treatment of bacteria that are resistant to other types of antibiotics that, again, that produce this beta-lactamase enzyme and destroy the penicillin molecule. The reason that methicillin is now sort of known a little more widely is because of its association with what's called MRSA. MRSA stands for something. It stands for methicillin resistant Staphylococcus aureus. So a MRSA infection is an infection with a strain of Staph aureus that is resistant against methicillin. So this is a particularly bad bacterium. It's resistant to a lot of antibiotics, including this drug methicillin that was reserved specifically for these dangerous microbes. Now, the cephalosporins are closely related to the penicillins. They are also cell wall synthesis inhibitors. The cephalosporins contain a beta-lactam ring, so they are considered beta-lactam antibiotics, but the ring is a little bit different in its structure. Cephalosporins are semi-synthetic. They are based upon a natural molecule, but it's a molecule that's been modified. In fact, cephalosporins are constantly being introduced onto the market, new cephalosporins. By the nature of the molecule, they can be tinkered with in lots and lots of different ways. And so we have what are called first generation cephalosporins, the originals. Those were modified to create the second generation cephalosporins. There are third generation cephalosporins and so on and so on. There are lots of them on the market, and they are continually being produced in order to stay one step ahead of antibiotic resistance. You've probably heard of some cephalosporins. You may have even taken some of these drugs. These include things like Keflex, and Ceftin, and Cefzil, and Suprax. Again, you may have heard of some of these.